and hi to everyone. And as promised, I will come up with a video for our module 7. So here we're going to see why we need to learn on our module 7, which is what topic? It is input output and a storage system. So first, of course, we're going to look into output and how the correlation also between input output and also storage system. And the objective or why we need to learn module 7, which is input output and storage system, first is to understand how the input output system work. You already learned the processor, you already learned the memory, you already learned the register, you already learned what else? The cache. And now it's turn for you to learn input output, including the input output method and also architecture. So everything in this like a world, a system, we need to have the architecture. To familiar with storage media and the differentiations in their respectively format. So under storage system also there are a few format that you need to know, and here we're going to learn it in our module 7. Next is to understand how RAID improve this performance and reliability, and which RAID system are most useful today. So we're going to look what system that normally used and frequently used. Be familiar with emerging data storage technologies and the barriers that remain to be overcome. So that is on the objective part, why you need to learn and what is the outcome that will be at the end of our module 7. So in our module 7 is like two short topic. We have basically the main two thing is the input output architecture and also data storage. But on top of it, before you go deeper, you're going to learn on the introductions. After you already done everything, we're going to summarize our input output and storage system. So let's take a look into the introductions. So all computer have input output device. As we already look, if you still remember that what last time when we first and at the beginning of our study, we already look the process of computer. What is the 1 2 3 4 right? 4 process or elements for your computer. So some of that is the input output. You need to have input and then you need to have the output. And yeah, of course, later on you have the processor, and another one is the memory. So this is how basically it's going to be look like for your computer system, and this is a correlation between each other on the memory or storage part. So this is the input and this is the output. Last time you look into like this, but now you're going to go deeper to the input output device. And all computer need to have the input output device which is connected to them, and to achieve good performance, input output should be kept to a minimum. In studying input output or I/O, okay, I'm going to call it as I/O also only. So we seek to understand the different type of I/O devices and well as how they work. So we're going to look into several type of I/O and how they're going to be worked and to be used for your computer. Data storage and retrievals is one of the primary functions of your computer system. So this one also, because we have a data storage over here, which is same goes to the memory things, which is a storage part. One could easily make the arguments that computers are more useful to us as data storage and retrieval devices than they are as a computational machines. So you can try to look back if you don't understand, but basically it's just like introduction, why you need to learn on input output and what is basically input output and etc. So now we're going to proceed with our modules subtopic 7.2. So in our 7.2, we're going to learn on I/O architecture. So in our I/O architecture, we're going to look into the overview, I/O and performance, I/O control methods, I/O bus operation. So I/O is defined as a subsystem of components that move coded data between external devices and a host system consisting of a CPU and main memory. So I/O subsystem include, but not limited to this list, but this is the must or include subsystem in your I/O. So some of that will be a block of a main memory, which is devoted to I/O functions. Buses, this one we also already learned, right? Move data into your to and out of the system. Control modules in the host and in peripherals devices interface to external components such as keyboards. Last one is cabling or communications link, which is between the host system and the peripherals. So this is some, because it's not limited, so you can have another, but this is the must thing that you need to know for your input output subsystem. This is the model of I/O configuration. You can see a lot of I/O is needed, like including the I/O bus, I/O module. Of course, you can see that this is all the input output device, like your monitor as the output device, keyboard as your input device, and you need to have the interface device for you, like you're going to connect them together, because this is like external something equipments. So you connect it into the device interface and connect it into the input output module. So this is the device adapter circuit board, or called as adapter card. And throughout all of this is your motherboard. Your motherboard, of course, you're going to see that you consist of the CPU. If you remember last time, the main entity, the main component for your motherboard is the CPU. And then you're going to have the main memory, and your memory bus over here, which is connected between CPU and your memory. And if you want to connect your input output with the main memory and your CPU, you need to have a I/O bus also. Here you're going to generate, and later on you're going to see deeper what is inside your input output module and etc. So there is also another device interface if you want to connect to another equipment like a printer, a disk, and etc. Okay, here is you going to see the things on our input output model configurations. First, you're going to have like a block of your memory. Second is a I/O bus, and third is control module. Fourth is the interface. You can see you have several device interface, but everything over here is a adapter card. But this one is adapter card. Sometimes it's a different kind of adapter, but it is throughout. It is a device interface. And lastly, the cabling. So this is 5 big important thing for a model I/O configurations. So you will like need to memorize what these 5 important uh, model in input output configurations. Now we're going to look into the I/O control methods. So under I/O control methods, you're going to see that there are few methods that you need to, and also you can use in your computer system for the input output control methods. So you're going to see that input output control, it can be divided into 4 general, which is program I/O, interrupt driven I/O, third is direct memory access, or it can call as DMA, direct memory access, and lastly channel I/O. So after this, you're going to look into one by one, and along of this also you can see there is a several different kind of way for each of these methods. First, we're going to look into the program I/O. System devoted at least one register for the exclusive use of each input output device. Program I/O sometimes refer pulse I/O. It can also call as the pulse I/O. Pulse I/O. The CPU continually monitors each register, waiting for data to arrive. And as I mentioned that everything's in this world, technique, people's equipments, they're going to have the advantage and the disadvantages. First, the advantage is simple and less hardware. So this is for your first method. And for the disadvantages, it wastes of processor's time, which is processed faster than I/O. Overhead in pooling instead of the actual data transfer. Second is worse for higher bandwidth I/O devices. So this is on the disadvantages for your programmable I/O. Okay, interrupt driven I/O. Instead of CPU continually asking it attached devices whether they have any input, the devices tell the CPU when they have data to send. So the device itself, okay, going to tell and inform CPU when they have data to send, to transfer, and etc. Interrupt are usually signals with a bit in the CPU flags register. So it's called as the interrupt flag. I guess you already look several kind of flag. So these here, the interrupt flag are generated under the methods of interrupt driven IO. Once the interrupt flag is set, when you see your flag is equal to 1, macam tu kan, so it's going to call as a set. The operating system interrupts whatever program is currently executing. So if let's say you are like opening your Microsoft Words, so it's going to execute, saving the program state and variables information. Of course, it's going to save, right? Because if let's say suddenly it's corrupt, so whatever you are typing, then it's going to lose. So this is the purpose, like you're going to of course you're going to execute, but on top of it, it's going to save the program state and whatever values that already informed. And after the CPU has completed the servicing the IO, it restore the information itself from the program that was running when the interrupt occurred and the program executions resume. So the example of the words, when let's say after your CPU complete on the serving the IO things, so it's going to restore back. Then that's why sometimes kadang-kadang you punya words corrupt ke, and then there is another few program that suddenly execute without your permissions. So then you can see it's going to restart back, isn't it? It's going to restart back and execute back, and then it's going to restore whatever information, whatever saving data that you did not save it manually. So automatically it's going to be like save the state, so it's going to restore whatever you did not save manually. So here is the architecture for your second method, which is the IO subsystem using interrupt. So this is the interrupt driven IO. So what you're going to see over here, you have first is the every peripherals devices in the system has access to an interrupt request line. So this is the first and like starting. As you know, keyboard and mouse is the input devices, isn't it? So you're going to see that this is the peripherals device in the system has access to an interrupt request line. So you're going to interrupt. Maybe your keyboard are typing some things, control X ke, which is you interrupt the program. So it going to send the request or the information to your interrupt controller, and then the controller signal the CPU. So you can see it's going to send the signal or the request to the CPU when any of the interrupt line are exited. Last thing, the CPU is ready, exits the INTS signal. So you're going to see over here, is going to be ready and accept back the INTA signal to your interrupt controller. Of course, like something will happen on top of your program, is going to corrupt and etc. So third method, what method that you're going to have is direct memory access, or DMA. So please remember, DMA stand for the direct memory access. So with both program I/O and interrupt driven I/O, the CPU move data to or from the I/O device. When a system use DMA, the CPU overload executions of the tedious of input-output instruction. So you're going to see also the different. Last time you're going to have the flow or the block control for the input-output subsystem like this for your interrupt. But now you're going to see on the DMA configuration how it's going to be like. So before that, you need to see that there are several effects. To effect the transfer, CPU provide the DMA controller with these three things. Okay, so first is the location. This is that CPU will provide. So CPU will provide the locations of the bytes to be transferred. Second, number of bytes to be transferred. And lastly, the destinations of the destination or the memory address. The destination device or a memory address. So only these three CPU will provide for DMA controller if you are using direct memory access. Okay, here you can see, first of all, you're going to have the DMA and the CPU share the bus. So you're going to see you have the CPU and your memory, and you're going to share the same bus over here. And of course, if you look, you're going to have the similar thing like previous, which is under your interrupt. You're going to have the keyboard, the mouse as the input. You're going to have like a disk, a printer. I guess this one is the not the input, but this is if let's say it is scanner, it can be. So printer is normally output, right? So you can see you're going to have like a similar device. You can going to have printer again. Device internet, but maybe it is going to connect because this one is output, right? This one is the input, or this also can be output because it's going to be like normally it have the readables and what readable, isn't it? So you can open it and then you can rewrite and etc. So of course you need to have something in between. You cannot like direct to your CPU, to your computer. You're going to have the device interface between each, like whether it is input, whether it is output, right? So then it's going to connect to your DMA. So on top of your DMA, how are you going to communicate with your CPU and your memory is going through the data bus. So there are, after you communicate through this line, then your CPU will return it back for these three things that we already looked over here. On the location, on the number of byte. So you're going to see a device name, number of byte, and then memory address. So device name is the locations. Memory address also can be as the device destinations. So here is the flow. We have the data bus share. And another one is the DMA run at the highest priority. And still memory cycle from CPU akan cycle stealing. And last method that you need to know is channel I/O, channel input output. An intelligent type of DMA interface known as an I/O channel. So DMA I/O requires only a little less CPU participations than does interrupt driven I/O. So it's going to compare with several another second, isn't it? Second methods. So you're going to see there is the advantage and the disadvantages. For the advantage is fine for small and single user system only. So if you have a bigger multiple user system, it's going to be like having some troubles. So over here, not scale well for large multi-user system. So if you are using a mainframe computer, it is not going to be used. You are not going to use the channel I/O. Okay, here under our channel I/O, you're going to see also the configuration later on. But before that, under I/O channel, it consists of one or more I/O processor that control various I/O pathways, which is called as a channel path. And our channel path can be divided into two, which is multiplexer channel, or another one is our selector.
It's 1 hour.
Selector channel. Our multiplexer channel paths for slow device can be combined, which is multiplexer, under one controller with faster channel. So the example is terminals and also printers. But for selected channel path for fast device only. So if let's say you have several device that connected to your computer, so for the selector channel paths, you're going to pick the fastest. So if let's say you learn on path planning later on, I guess not now, you have a system. If you need to find your parts, okay, I give you this daily activities that you can imagine about the parts. Okay, if you are using a waste, I don't know whether you already uninstall it because of the issues of Israel and Palestine. But if let's say you're going to use Google Map, when you use the navigation, let's say you want to go to somewhere like maybe from your home to Tesco. So you're going to find the route first, isn't it? It's going to find the route, and it's also based on your selection. Normally, by default, it's going to find the faster, which is there is no jam, there is no like any kind of event throughout, like accidents or etc., throughout the route. So it's going to pick the fastest. But you can also select on the kilometer, how far the destination with your current point. So that is on the paths. But normally you going to like in the system, normally it's going to be pick the faster parts, or the faster parts. So your system also, if let's say you are using a Waze, a Google Map navigation, by default is going to pick the faster, although sometimes it's like far rather than others route. But throughout that event is no accident, no traffic jam, so that's why it's going to be picked, because you're going to reach to your destination faster rather than other routes. So that is on the parts, if you learn about part planning and etc. Same goes to a channel. So our channel parts, if you have the selected channels, you're going to pick the faster device. And here is our channels IO configuration for your last method. So you can see over here, you have, first of all, you're going to have the small CPU IO, which is small CPU. But before that, you're going to see like you're going to have this is over here, this tab, and then you have a printer, and of course basically you're going to connect it with your processor before you going to directly to your CPU. So last time, if you see, it is not called as IO processor, but on top of it is going to be like device interface. Another method also, it's this one is interrupt controller. So this is all the device interface and adapter between your device, input output device, and also your system like CPU and etc. So in between there are several things that you need to know. For this channel IO, is using the IO processor. For the DMA, it's called as device interface, and another one is your interrupt driver. You're going to have the interrupt controller. Now, first of all, okay, you already look into IO, which is processor CPU. And then second, you're going to have the IO bus, help to isolate the host from the IO operation. So this is the flow, but I don't think that is going to be like ask you to redraw, or because there is a lot of configurations picture, I guess, on also a graph that you need to remember, right? So the examples, copying file from your disk to tab. So you're going to copy everything from your disk. Let's say from your CD, there is a open movie, and then you want to paste it and transfer it into your tab device. So IOP, which is a small IOP, use only system memory bus to fetch its instruction from the main memory. So you're going to go through to your I/O processor, and then you're going to go through to your memory bus to pick any kind like correlation between the I/O and also your memory. Okay, you can see the flow. Direct to the I/O processor, and then of course you're going to have like I/O bridge to connect your I/O processor with the CPU and main memory to your memory bus, and your memory bus will be go to direct to your memory, and then after that you're going to see it's going to come back again to the I/O processor, and then it's passed to the tab. A reminder transfer is affected using only I/O bus. So I/O bus operation. What is I/O bus operation? The memory bus and the I/O bus can be separate entity. So you can see over here, this is memory bus, this is I/O bus. It can be combined, it can also be separate entity. One good reason for having memory on its own bus. Why? Because it's better for you to have memory bus separate with I/O bus, because memory transfer can be synchronized using some multiple of CPU clock cycle to retrieve data from memory. Never end issues of the memory being offline that affect peripherals equipment, such as a printer running out of paper. So you can see after this, you can see that there are a list of the disadvantages for the I/O bus operations. So I/O bus, on the other hand, cannot operate synchronously with the I/O device, cannot always be ready to process the I/O transfer. But you can see also I/O controls a circuit placed on the I/O bus, and within the I/O devices negotiates with each other to determine the bus to be used. Because this handshake takes place every time the bus is accessed. I/O buses are called as unsynchronized. So here there is a two type of transfer I/O operation. One is asynchronous, one is synchronized. So for synchronized, it's called as a memory bus, and for the unsynchronized is I/O bus. So synchronized require both the sender and the receiver to share a common block for timing, and then unsynchronized also require a clock for bit timing and to delay the signal transitions. To distinguish synchronized from unsynchronized transfer will become clear after we look at the next example. So here, okay, this one is an example. So you're going to see that the DMA configuration showing separate address, data, and control lines. So this one, the example of DMA circuit, and the device interface circuits is more accurately represented by the figure over here. So if you go back to the DMA, you're going to like compare between each others. Okay, this is the example to write data to the disk drive. So here is a disk controller interface with connection to the I/O bus. So you have the data and address bus. So all of this is a bus. You're going to connect to your disk, you're going to connect to your disk controller, address decoder, cache, I/O controller, and disk decoder. So you're going to have the first data bus. Everything, let's say you have something that you want to write data, and you're going to write it into your disk. Let's say you just want to write hello. You want to write hello. So this is the data, and you want to write it into your disk. First, of course, you're going to go through using your data bus. And what is another important thing is your address bus. This is the one that going to inform you where you're going to go and your destination, and about the address also. And last thing that is important is on the clock bus. So this is the clock bus. So of course, if you still remember everything's about clock, going to trigger some things. If let's say like a positive clock or negative clock, I also already forgot, and it's going to control. So that's why it's going to connect it to the I/O controller. It's depend on your request, whether it's ready, reads, and of course on the clock itself. If your clock, let's say, it's not trigger anything, so there is nothing happen to your I/O controller and etc. So this is the flow. Basically, it is too long in sentences, so you can just try go through. Basically, it is the flow how you're going to write to your disk drive. Maybe you can try to read it first before you let's say I explaining it in terms of long sentences also. So this is write this operation. You can see you have the bus clock. This is not a must, okay, because there is a several way. Let's say for a clock, maybe at T1 maybe it's going to be low. It's depend. So in this example, it's going to be look like this. So what happened is the flow is depending on this first step is DMA circuit plus the address of the disk controller on the address line, and rest the request and write signal. Second is what happens. So it shows also with the example like one by one. So you can see the bus rarely show the separate, usually as a group. And this one is not rise. Basically this is the shows to you what is happened to all the clocks and also signals that given. So let's say over here, what is represent for this, which is a call. Last time, if you are still remember on your digital logic, you call it as a low, isn't it? And if it is like at this point, it's going to be high. You have low and high only. But now you're going to see in your input output, it's called as a not rise or fall. Fall in instantaneously. Small time to stabilize signal. And okay, what else? Okay, this one. Signal on bus only change during the clock cycle transition. This one we already know. because if let's say the clock is not changed, nothing will happen also to your output signal. So this one I guess you already know because we already learned in our DL. And if let's say there is something like this, what is the meaning by this? So you need to know this is shaded, which is the bus is inactive. Okay, the bus it is inactive. And if let's say there is no colors like this, it's white colors, it is called unshaded, which is the bus is active. Okay, this one is your bus request and etc. This one is data and so on. Okay, now next over here. Okay, this one is rest. If let's say you can see, you have the cross line. You have the cross line over here. You have also another cross line here. It calls as a cross line. What happened is bus transitions, active or inactive state. So it's depend. But this is the bus transition. Okay. This is a bus transitions and etc. So you're going to remember all the things. What is this at the beginning? What is this also it is similar. Shaded, unshaded, clock and low and rise and etc. Okay. Okay, this is now coming up with the flow. Flow like mentioned over here. 1, 2, 3, 4, 5. So this is all the flow. I don't want to read it because yeah, you can also read, right, sentences. And first you're going to see DMA place address of the disk controller on the address bus. Second, controller check address bus. Third is one disk available for writing. So you need to wait first because you're going to be like ready. When it's like trigger you high, you're going to be ready or available. And then you're going to see also handshake between DMA and controller complete for one single clock. Fourth is DMA place data on data bus. You just place it first because at this phase you're going to see you are inactive, right? So it's still like ready. So you just place it on the data bus. And then the fifth is drop when byte transfer from data bus to your disk. So you can see drop when byte transfer from your data bus to your disk. One writing complete. Other devices may use the bus. Okay, because you already finished with your cycle, complete one cycle. So then you're going to complete and device might use the bus, another different kind of device that available. So this is all the 5 steps shows also in sentences. I guess in sentences you can be more understanding, and after you already understand and you go to step by step over here, then it's easy for you to memorize also. Okay, the bus operations in detail based on the previous timing diagram. So you have this time, you can see on top of this time, and what kind of bus signal that are using. Let's say for the first, this is like address bus, right? Address bus, right? So bus is waiting for writing. So this is all the informations in timing diagram or in the look like as a table. And that is only for your I/O architecture. Later on, you're going to see the storage, data storage, and it is not too hard for data storage, and we're going to finish our module 7. So I guess I'm going to stop for now because the video is already equipped longer in time. So we meet again in the next video and also next class. Okay, please stay safe, don't go anywhere, stay at home, and bye bye.